Let's go ahead and get started. So we talked about 2 types of reactions yesterday. We're going to talk about the other 3 types today. Okay. Do you guys remember what the 2 types we talked about yesterday were called? Don't say love story and breakup. Okay, combination is the first one, and then decomposition is the second one, okay? So they're basically the exact opposite of one another. Combination, we're talking about the love story, right? 2 things coming together to form one thing. And then, never mind. And then when we, get my train of thought back here, decomposition, we're talking about something breaking apart, okay? This is a breakup. We've got one thing and it's breaking apart into at least 2 things, sometimes more than that, depending on the compound, okay? This is where it starts to get a little strange. If we're thinking about these in terms of relationships. Let's see, where are we? We already did all this. We already did all this. Here we go. Okay. I'm going to show you this video first. And actually, just realizing the audio for this is not going to show up on the video. So if you're watching the video, I'll put the link and you can watch it. But I like this because it shows something that I can't really do in class. Plus, oh, and this is going to come through my headset. No, it's not. Okay, never mind.
But none quite like the thermite reaction.
Let me pause this for a second. The other reason I like this is because this guy sounds like Mr. Rogers. That's why we were watching Garden of Your Mind, before. If we have time, I'll show it to you. Okay, so this guy's doing a thermite reaction, so just watch this. This is an example of a single replacement.
We're going to fold into a cone. We're going to place a mixture of aluminum and iron oxide into the cone. We're also going to add some thermite starting mixture.
The thermite? Yeah, I can't remember exactly what that's made of. I'm going to have to look that up. But this is the part that gives it the actual heat that it needs to make this reaction occur.
Then going to place a piece of magnesium ribbon down into the mixture and move the explosion shield into place before we light the magnesium heat.
Yeah, sometimes if it gets too uncontrolled, it like melts through the floor. So I don't think that's a good idea here. You see how hot that gets.
Carefully lifting it out of the sand. This white hot iron is encased in a crucible of glass that has been made by melting the sand. You can see some of the liquid metal as it drips out of the glass. We're going to allow that to cool down, and then we'll chip some of the ceramic off the metal and take a look at it. Let's now use a hammer to crack off some of that ceramic. Here we see some of the crude ceramic that enclosed the metal. Here we see the metal, the pure iron that forms. Let's take a look at the chemical equation for this dramatic reaction.
I love this guy.
Here we see that the iron oxide is reacting with the aluminum in a single displacement reaction. The aluminum oxide is produced, and there's the iron metal that you saw in the molten state. And of course, a large amount of energy in the form of heat and light was released.
Okay, so that's an example of a single replacement reaction. I know, everyone wants to watch this one instead of the one I showed you. I wonder if Mythbusters have ever done thermite.
Oh yeah, split a car in half.
Did they really? Oh my gosh, that's cool. Yeah, maybe I'll have to show you that one at some point. That sounds pretty cool. Okay, so now we're on single replacement. Here, let me turn the lights back on. Watch out, this is going to hurt. Told you. Alright, so this is the definition of single replacement right here. Okay? One element is replacing another one in a compound. And I know I keep promising you guys that we're going to do this potassium and water thing. It's going to happen. There's a better time for us to talk about that than right now. Okay? And it'll be second semester. But I promise we're going to do this. Are we ready? Okay, the general form of this equation is going to look like this. AB plus C gives us CB plus A. Okay, so like I said, this is where it gets a little more interesting. Single replacement reaction is like, have you ever seen the show Cheaters? I don't think it's even on anymore, okay? Yeah. The only reason I really even know about that show is because I used to live in Dallas, and I'm pretty sure that that's where it was filmed, okay? So, real classy city I was living in there. But basically the idea is, if someone suspected that their significant other was cheating on them, then they would go, you know, with a camera crew and try and follow them around and catch them, you know? Oh, look, you're out on a date with somebody else. And then there would usually be some public confrontation, and there would be hitting and stuff like that. And, you know, good TV, right? So, yeah. So it's like that, okay? This element C right here decides it wants to be in a compound, and so it kicks out the A and then forms a compound with B, okay? So that's single replacement, okay? Now, the example of this, the potassium and the water, the way that this works, and this is what you're going to write for your example here, K plus, I'm going to write this kind of weird because I think it'll help you see it better. That's water, right? Okay? Yeah, I know what I told you before, okay? But I'm just in this particular instance, okay, it works better because you can see the potassium is now going to kick out this front hydrogen here, okay? And so then what do we end up with? KOH and H. H2, good. Hydrogen's going to be all right, right? Because it forms a diatomic molecule, so it's still not by itself. Happy ending for everybody, kind of. Yeah, okay, there you go. Is that how you think of the diatomic molecules? They're just best friends. Okay, that's nice. Okay. A pet? Okay. All right. Anyway, we need to balance this as well, okay? So how would we balance this one? Yeah, this one's a little tricky. We've got kind of an odd hydrogen situation going on over here, so I think if I put a 2 there, that's probably going to be a good thing. That makes it 4 hydrogens instead, and then I could put a 2 here, and then I need to put a 2 here to balance my potassium, okay? If you can't do that in your head like that yet, that's fine. You can still use the tally method, and that works just fine. Okay, we ready? Next, we need to talk a little bit about the activity series, okay? So I know I gave you way too big of a space for this, okay? But the activity series, we're basically talking about, well, if this is a cheater's relationship here, then lithium up there, you see on the top of the chart, lithium is the big weightlifter guy who's walking around on the beach kicking sand in the face of the little guys and taking their girls, right? Okay? That's lithium. Lithium is the most reactive. That's the one that's really strong. I don't know. I mean, I just have to keep myself entertained here, right? I'm teaching this 7 hours a day, so. All right. So lithium is the one, it's the most reactive, so it's going to replace pretty much anything, okay? It's going to be the one that comes and steals from the compound, all right? Poor Silver here, well, he's the one who always gets sand kicked in his face. He always gets his girl taken away, right? And so Silver is usually by itself. Does that kind of make sense? Yeah. Okay, because silver, right, that's why we use silver in jewelry, because it doesn't react with much, right? So that's the idea of the activity series. It just talks about how reactive they are, okay? you need to use that activity series to figure out if something will replace something else in a compound. Okay? And I'll show you how to do that. And I'm going to give you one of these activity series for yourself. You get to use those on quizzes and tests and all of that, so you don't have to memorize that chart. So this first one here, zinc plus sulfuric acid. What's going to happen here? The zinc is by itself, so it's probably going to try to replace something. What is it going to try to replace? The hydrogen? Okay, that makes sense to me. So the zinc is probably going to replace the hydrogen here. Okay. Now, what you have to keep in mind, the cation, a cation is always going to replace another cation. Okay, or another way to say that is a metal always replaces another metal. Okay, so zinc's a metal. The hydrogen here is acting as a metal. It's got a positive charge, so the zinc's going to replace the hydrogen. Okay. If it can, that's the question we've got to ask. So let's go back to the chart here. Is zinc strong enough to replace hydrogen? Okay, zinc is up here, right? Hydrogen's down here. So yes, it is strong enough. So since this is actually going to happen, we can write this reaction. It's going to be ZnSO4 plus, once again, we have H2. That seems to happen a lot to hydrogen. And this one's already balanced, right? Now, the second one down here, this is a little tricky, okay? Chlorine is the one that's by itself here, even though it's diatomic. It's just one element. So what is chlorine going to replace? Okay, are we in agreement on that? Now, how do we know chlorine's going to replace the bromine, not the sodium?
Sodium's very reactant.
Okay, well, there you go.
Oh, yeah.
Okay. So it has to do with the metals versus the non-metals, right? Okay. So chlorine's a non-metal, bromine's a non-metal. Non-metals replace non-metals. Okay. So this is kind of the opposite. The chlorine's going to replace the bromine. We end up with NaCl. I've been having students say this all day. Why not NaCl2? Okay. This is diatomic over here when it's by itself, right? But when chlorine forms a compound, you have to think about what charge they have. Sodium's a 1 plus, chlorine's a 1 minus. That's going to be NaCl, right? Plus, which one? Br2, right? Okay, the bromine's the one that gets kicked out. And bromine's also diatomic. Now this one we have to balance. All we have to do here is put a 2 in front of the NaBr and a 2 in front of the NaCl. And that should do it. Okay, does that make sense? Alright, moving on. Couple more examples here. I'm going to let you, well, you know what? I was going to say I'd let you try these on your own. Well, here, we'll look at the activity series, and then I'll let you try them on your own after we check it, okay? So, the iron is by itself. What is it going to try to replace here? The lead, okay? So we just have to figure out, will it replace the lead? So looking at the chart, will the iron replace the lead? Just barely. This is going to be quite a fight on the beach, right? But it will just barely replace the lead. Okay, so that one actually is going to happen. The second one I'll just tell you is going to happen because chlorine's not on your chart. But what is the chlorine going to replace here? It's going to replace the iodine, right? Because those are the anions or the nonmetals. And then this bottom one, your little hint on this one is think of water as HOH again. Okay? And then if we come back to the chart, will calcium replace hydrogen? Yeah, calcium's way up there, right? So it will definitely replace hydrogen. Okay, so knowing all of that, see if you can figure out those three and make sure that you balance them after you get them. Okay, for the sake of time, let's go ahead and talk about those two. Or three. There are three of them. If I can find it. There we go. Alright, so the first one here, like I said, I forgot to tell you what charge iron would have because it's hard to know because it's in the middle, right? So if this was a 2+, then this would end up being FeNO3 plus Pb. And the nice thing about that is you don't have to balance it, okay? Iron could also have a 3+ charge, but we'll go 2+ on this one. Everybody okay on that? Okay, and again, remember, don't think about what subscript this nitrate had over here. Okay, think about when it combines with the iron, what subscript is it going to have. Okay, the second one here, this really is very similar to another example we already did, so I'll just put this one up here. Hopefully you guys are okay on that one. Any questions about that one? Okay, and then the last one here, as long as you're thinking about this as HOH, then the calcium just replaces the hydrogen there and ends up making what? Okay, CaOH2, right? Because calcium has a 2+ charge, and then we end up with the hydrogen left over, the H2. Why is it OH? Because the calcium, see this first hydrogen here? You can kind of think of it as the calcium replacing that hydrogen. Okay? Oh, okay, that's, remember, you don't think about the first part of the equation here, okay? You think about when calcium and hydroxide come together, what's the ratio going to be, right? Calcium's a 2+, hydroxide's a 1-, so you crisscross, okay? And Abby, I think what you're having trouble with is now we have more than we had to begin with, right? Okay? But that's why you balance the equation at the end. That makes sure that we have the same number of atoms on each side of the equation, okay? So then I'm going to put a, let me erase some of this stuff. I'm going to put a 2 right here. So it takes 2 water molecules to make this happen. And then it all works out. Okay? Alright, that's single replacement. Now we can move on to double replacement, and here's where it gets really weird. I'm also showing you this demo on a video, and I like to show you these demos in, live if I can. The problem I've had with this demo in the past is when I do it, there are disposal issues because I'm making lead iodide, and we're not supposed to pour lead down the sink. It's bad for the children. So yeah, I just don't want to deal with that anymore. We literally just cleaned these cabinets out last year because we had some science teachers at some point put beakers of stuff down below there and had no idea what it was, and so, that's kind of dangerous. So I don't want to shove something down there and then 20 years from now someone's like, oh, wonder what this is, and then it poisons them. So, so anyway, yeah. I'm just going to show you this video and let the guy who made the video worry about the disposal issues, okay? Yeah, I don't know. Yeah, I'm not sure if that's going to work. Okay, this one does not have any sound, so I'll just kind of describe to you what's happening here. Maybe I'll turn off the lights again. Basically what we're doing is adding lead nitrate and potassium iodide. These are both clear solutions. Yeah, and that's the precipitate. That's lead iodide. So obviously a chemical reaction is happening here, right? 2 clear liquids together making a yellow liquid. That's not what we would expect. And then it just kind of goes on for a while, and I think it seems like they start shooting in slow motion, which is maybe a little more dramatic than it needs to be.
Especially when the thing...
Whoa! There it goes. So, anyway, you get the idea there. That's a double replacement reaction, okay? That's it. Yeah, I'm sorry, no explosions that time. Double replacements usually don't involve explosions, so. Okay. So here's a double replacement reaction. Okay, watch your eyes again. You don't, that's not physically possible, but, you know, watch out. Okay, here's where it gets even a little bit stranger, okay? And we're going to try and keep this PG here. So double replacement reaction, have you guys ever seen the show Wife Swap? Okay? Yeah, it's kind of like that, right? So what's happening is you've got two compounds here, and the parts of the compounds are switching places, okay? So the general form of this one, this would be AB plus CD gives us, you have to be careful how you write this, it's going to be AD plus CB, okay? And I'll show you why in a second. Well, I can show you why now, I guess. This A and this C, okay, those are the cations, those are the metals. You're going to switch those, and that's really the easiest way to do this, okay? So you see how those switch places and you end up with AD and CB, okay? Yeah, okay. So, yeah, you can switch these around. I mean, these can be flipped around, right? You could write, if that bothers you, then you can write the CB first and then the AD. Sorry about that. No, I'm just saying you can flip these around, right? You could have the CB first and you could have the AD second. Either way is fine. Okay? I just wasn't paying attention when I wrote that, yeah. So, okay, so let me show you the example here. This is potassium carbonate and barium chloride. Don't write this down yet. I'm just using this screen because there's more room. Potassium carbonate and barium chloride. Okay, what's going to happen here?
Okay.
Okay. Right. So the potassium's the metal, the barium's the metal, right? So those are the ones that are going to switch places. So then we're going to end up with, okay, now here's where you have to be careful, alright? Because it's going to be K and Cl combining, right? But how are they going to combine? It has nothing to do with what was over here, right? It has to do with the charges. Just KCl. 1 plus, 1 minus, it's going to be KCl, okay? Plus, you have to remember what barium's charge is, and you have to remember what carbonate's charge is, okay? Barium's charge is 2 plus, okay? And then carbonate, you might not remember that one, it's on your chart, it's 2 minus, okay? So you just need one of each of those. BaCO3, good. Now, the other thing, well, I guess we got to balance this too. This one's pretty easy to balance. All we have to do is put a 2 in front of the KCl. Okay? And then you have this on your notes. Let's see here. It says for a double replacement to occur, one of the following 3 things has to be produced. What you're going to write there is precipitate, a gas, or water. Okay, one of those 3 things has to happen. Yes, ma'am. You guys remember what a precipitate is? It's a solid that falls out of the solution, right? So a solid is essentially the same thing as a precipitate, okay? Now, you have no way of knowing this yet. I'm going to teach you this in a couple of days. But the barium carbonate is the one that's the solid for now. I mean, not for now. That is the solid, okay? But for now, you wouldn't know how to do that on your own. I'm going to give you a bunch of rules so that you will be able to figure out exactly which one is going to form the solid. Okay, so that's the wife swap. That's the double replacement. we'll do practice on a couple more of these together, and then I'll let you try these on your own. So silver bromide gets formed as a precipitate here when we swap these two. Okay? Same thing's going on here. Calcium's going to switch places with the silver. So then what's silver bromide? Well, the silver bromide is AgBr, right? Now again, the temptation here is to write AgBr2 because there's a 2 over here, okay? Pay attention to the charges on the elements that are forming the new compound, okay? And this is our solid. They're already telling us. What's the other thing that's going to form here? I'm not sure. Oh, you got the N and the C mixed up there. Yeah, CaNO3 Yeah, good. CaNO3, ran out of room. CaNO3 okay? And then we're going to have to balance this one also. Let me clear this out. This is messy. 2 here, and a 2 here, and that should do it. Okay, and then the last one here, well, it tells us already we're making H2S gas. So that's going to be one of our things. What's the other one? Okay, this time you can figure out what the iron is. What charge does that iron have? How do we know 2?
Because chlorine. Because sulfur has a 2 and it was combined.
Okay,
Oh, yeah.
it was combined with sulfur in a 1-to-1 ratio over here, right? So that's Fe2+. So it's going to be Fe, what? Cl2. Good.
Is it okay if you have like the different things?
Yeah, if you have FeCl2 over here and H2S over there, that's fine. You can switch those. No, that order doesn't matter. Yeah, no, it really doesn't matter. Oh, no, it's not. We should probably balance it. Oh, this one's easy. Put a 2 right there. That the chlorine was a 2 there? Okay, because I looked over here and I said, okay, this iron is combined with sulfur. I know this sulfur is a 2- always, right? So this iron must have been a 2+. Okay, so then FeCl2. Alright, now I'm going to let you practice a couple of these. I think, where are they? Oops, I just showed you the answers. Don't look. No, I didn't. Didn't I give you some extra practice on these? Okay, they're just not on here, I guess. Okay, so see if you can do these last 2 on this sheet on your own. These are a little bit trickier to balance. And remember, think about what charge they have when they form the new compounds, okay? So practice those for a minute and then we'll talk about it. Yeah, that wouldn't be good. Okay, so back to this. Let's talk about these couple here. Where are we? We're past that. Oh, okay, here they are. They actually were on here. So this one right here, now I'm going to have to write super small. Yeah, there we go. I'll just write above it. Good idea. And then I'll write below this one. It's perfect. All right, so when these switch, we're going to end up with NaNO3 plus Fe what? OH3, right? Now how did I know OH3? Okay, good. So it took 3 of the nitrates, which each have a 1- charge, to balance with the iron, okay? Now the other thing, if you had seen this, they actually tell you on this one. I didn't tell you on your sheet because I wanted you to figure it out. That's a solid, okay? So, let's see here. We need to put a 3 in front of this and a 3 in front of this, right? Is that it? I think that's it. Okay, and then the next one here, this one's a little bit tricky just because of the way the charges work out. So we're going to have HNO3 as one of the things here, plus, anybody figure out what this compound's supposed to be? Ba3, PO42, and that's the precipitate, so that's the solid. Why is it 2? So if you have Ba is a 2 plus, right? PO4 is a 3 minus, so when you crisscross those, Ba3, PO42, okay. Alright, and then you have to balance this one. I'm going to have to put a 3 in front of this barium to balance my bariums. That gives me 6 nitrates, so now I have to put a 6 here. And then if I put a 2 here, I think we're good. Okay? Alright, sorry, we're almost done. And then we won't take notes again for a little while, okay? 2 days, I think 2 days of labs, Friday and Monday. And then we really will probably light our hands on fire on Tuesday of next week. Yeah, try not to burn your eyebrows off for Thanksgiving. That would be embarrassing with your family. Right. Okay. Last one is combustion. I don't really have a relationship analogy for this one. Okay?
Oh, I bet
People have been trying to figure it out all day. I'll show you the general form, and you can decide if maybe one idea works.
I have an analogy, but I don't think
I don't think your analogy is probably going to help remember exactly what happens in a combustion reaction. Yeah, see, that's the problem. Everyone's like, oh, combustion. That's like if the relationship goes up in flames. But that doesn't help me remember that combustion produces carbon dioxide and water, right? So, yeah, baby. Okay, let me show you the general form here, okay? Are you guys done with the definition yet? Okay. So, the very broad definition of combustion is anytime you're burning something in the presence of oxygen and it produces heat and light. We're going to use kind of a more narrow definition for most of the ones that we do. Usually our combustions are going to be burning organic compounds. Okay, what do I mean when I say organic? Leaves are organic. It has carbon in it, and usually carbon and hydrogen. Okay, so that's organic. So our general form of the equation here is going to be CXHY plus O2 gives you CO2 plus H2O. Okay? Now the CXHY, that just means you can insert whatever carbon-hydrogen compound you want right here. Okay? This is the general form of the equation. Yeah, this is not the example. Okay? But the thing is, all combustion reactions really look alike. Okay? This last part right here, the O2, CO2, and H2O, that's always the same on any combustion equation that we're going to write in this class. Okay? It's always going to be plus O2 gives you CO2 plus H2O. Okay? So the example here is the Bunsen burner. And the Bunsen burners burn methane, which is CH4. Okay? So CH4 plus O2 gives you CO2 plus H2O. See? It's the same every time. The only thing that changed was this first molecule. Yeah, it's really not that bad. And then we need to balance this, right? So if I put a 2 in front of the H2O, that would balance the hydrogens. And then if I put a 2 in front of the O2, that would balance the oxygens, right? I think that's right. 2, 4, yeah, 4. That's it. Okay. So that's pretty easy, right? The only thing that's really ever going to change is the one in the front. So this one you might just have to remember. Okay, couple examples here. If benzene reacts in a combustion, C6H6 plus O2 gives you, here we'll make a really long line here for our reaction, CO2 plus H2O.
If it's C6 plus NH6, make it CH.
Okay, good question. Listen up. Shh. This is actually a good question for everyone. Ben just asked, C6H6, can we reduce that down to just CH? Okay, and this is actually a molecule. Okay, in the molecular compounds you can't reduce. In the ionic compounds you want to. Okay, so this one it's just C6H6 because that's actually what's there. Now this one unfortunately is a little bit difficult to balance. We need to put a 6 in front of the CO2 to balance out the carbons, right? And we need to put a 3 in front of the hydrogen to balance those. But now I got myself in trouble because how many oxygens do I have on the right side? I have an odd number, right? It's 15 on this side, right? 12 from here and 3 from there. So we need to double the one that's causing the problem, which is the H2O right here. Can't do this without erasing it all, I don't think. 6H2O. Then we're going to have to change this. Oh wait, not have to change anything because we didn't have anything in front of this. I got to put a 2 here. That'll give me 12 hydrogens, 12 carbons. So now I have to put a 12 here. And then what would I put in front of the O2? You're going to have to keep going for a while, okay? There's 24, there's 30 oxygens over on this side, right? So we need a 15 right here, okay? Alright, we'll do the last couple examples. Actually, we only have one other example. You could probably finish this on your own, and then we'll start the lab first thing tomorrow, okay? No, on this stuff we will not take a quiz probably till after Thanksgiving break because we got to talk about some other stuff related to this.
I just want to say, Mr. Jones.
Hang on, don't say it yet. For all of you on the video, this is Mr. Jones signing off.